What if the solution to global warming was hiding in the sky above us? Not giant machines, not space megastructures, just clouds. But not the clouds we know. Engineered clouds. Brighter, whiter, more reflective. Designed to bounce sunlight back into space before it ever warms the Earth. It sounds like science fiction, but right now, scientists in the US, UK, and Australia are exploring this exact idea. And they believe it could cool the planet within a decade. Why reflective clouds? The numbers are stark. Global temperatures have already climbed 1.2 degrees Celsius above pre-industrial levels, a seemingly small rise that has triggered outsized consequences across the planet. Heat waves scorch regions once considered temperate. Wildfires erupt with devastating intensity. Droughts dry out fertile farmland, and floods overwhelm cities with increasing frequency. Each year, the records break, and what used to be once-in-a-century disasters now feel routine. Cutting carbon emissions is not just important, it is absolutely necessary. Every ton of CO2 prevented today makes the future more manageable. But here's the catch. Even if the entire world miraculously shut off all fossil fuel use tomorrow, the carbon already floating in the atmosphere would continue to trap heat for decades. The Earth's climate has momentum, and it does not stop on a dime. That delay means humanity may be forced to explore options beyond mitigation alone. This is where geoengineering enters the conversation. It is a field full of bold, sometimes controversial proposals to deliberately alter Earth's climate system. Some involve massive space mirrors, others suggest fertilizing oceans to absorb carbon, and a few lean on futuristic aerosols to cool the skies. Yet among these ideas, one stands out for being relatively straightforward, quick to deploy, and rooted in natural processes. Marine Cloud Brightening, or MCB. Instead of trying to remove greenhouse gases directly, MCB relies on physics to subtly shift how clouds interact with sunlight. By spraying fine sea salt particles into the atmosphere, certain clouds can be made brighter and whiter. Brighter clouds reflect more incoming solar radiation back into space, preventing it from being absorbed by the Earth's surface. It's like adding a planetary sunshade, not blocking the sun entirely, but nudging the balance just enough to buy us precious time. The core idea. Here's how it works. The oceans already hold the key ingredient, salt. Tiny salt particles are naturally lifted into the air by waves and spray, where they help shape the clouds we see over vast stretches of the sea. Marine cloud brightening simply takes that natural process and gives it a deliberate boost. The method is surprisingly straightforward. If you spray a fine mist of seawater into the atmosphere, the microscopic salt particles rise into low-lying marine clouds. These particles then act as nuclei, or seeds, around which additional water droplets can condense. The more particles you introduce, the more droplets form. But instead of making the clouds thicker in volume, this changes their texture. The droplets become smaller and more numerous, which increases the cloud's ability to scatter and reflect sunlight. The result? Whiter, brighter clouds that bounce more of the sun's energy back into space before it ever reaches Earth's surface. In essence, MCB doesn't change the sun or the carbon in the atmosphere. It changes the mirror in between. The physics is elegant in its simplicity. Spray mist, more droplets, brighter clouds, cooler Earth. This idea first gained attention in the 1990s, when atmospheric scientists began exploring low-cost, reversible methods to offset global warming. Unlike some geoengineering proposals that sound like science fiction, MCB builds directly on natural cloud processes that already occur every day over the oceans. That practicality has made it one of the most actively studied concepts. Today, small-scale experiments are testing whether the theory holds up in real-world conditions. Pilot projects off the coast of California and in Australian waters are deploying drone ships equipped with sprayers to release carefully measured mist. tracking how the clouds respond in real time. The results could determine whether this idea remains theoretical or becomes a vital tool in our climate toolkit. The science of reflection. At the heart of marine cloud brightening lies a deceptively simple concept: albedo. Albedo is a measure of how much sunlight a surface reflects back into space instead of absorbing. It's the difference between walking barefoot on a white concrete sidewalk in summer versus standing on black asphalt. One bounces the heat away, the other soaks it up. On a planetary scale, this principle matters enormously. Snowfields and glaciers, for instance, have a high albedo, reflecting the majority of the sunlight that hits them. That's why polar regions help regulate the Earth's atmosphere. By contrast, dark surfaces such as oceans, forests, or asphalt roads have a low albedo. They absorb sunlight, trap heat, and contribute to warming. Marine clouds fall somewhere in between. They don't reflect as much ice, but they still bounce back a portion of incoming solar energy. The cleverness of marine cloud brightening is that it tweaks this balance. By making marine clouds just a bit brighter, just a touch whiter, you slightly increase their albedo. That tiny increase means more sunlight is reflected back into space before it can warm the Earth's surface. The effect may sound small, but on a global scale, even small percentages matter. Climate models suggest that if cloud albedo could be boosted by just 1 to 2% across the world's oceans, the cooling effect could be substantial, comparable to rolling back decades of greenhouse gas emissions. In other words, this modest adjustment in reflectivity could act as a planetary thermostat, potentially buying humanity the precious time it needs to transition away from fossil fuels and scale up renewable energy systems. Key takeaway number 1: small particles, massive planetary effect. A single salt particle is so small it's invisible to the naked eye. You could hold a handful of seawater, let it dry, and never notice the millions of salt crystals left behind. But when those particles rise into the sky and seed clouds, their collective influence is anything but small. Scale them up by billions, spread them across thousands of square kilometers of ocean, and they become a force capable of reshaping Earth's climate. That's the paradox of marine cloud brightening. It harnesses something microscopic to influence something planetary. Climate systems aren't only driven by massive glaciers, sprawling deserts, or vast ocean currents. They're also finely tuned by the chemistry of aerosols, the size of droplets, and the physics of how sunlight scatters. Even the tiniest shift, making a cloud just a fraction brighter, can ripple outward into measurable global change. This sensitivity is both the strength and the danger of geoengineering. On one hand, it shows how small targeted interventions might help stabilize a warming planet. On the other, it underscores just how delicate the climate balance truly is. If minute salt particles can alter global energy flow, then so can pollutants, volcanic eruptions, or even unintended side effects of human activity. That fragility is what makes climate engineering both promising and unnerving. Marine cloud brightening is a vivid reminder. The fate of Earth doesn't always turn on giant forces alone. Sometimes it hinges on the smallest of particles. Magnified by the vast machinery of nature, it is proof that the boundary between stability and chaos in our climate can be as thin as a droplet of mist. Who's working on it? Marine cloud brightening isn't just an idea on paper anymore. It's a field with real experiments, real researchers, and growing global attention. Several groups are leading the charge, each approaching the problem from slightly different angles, but all with the same goal: to test whether brightening clouds can safely cool our planet. At the University of Washington, scientists run the Marine Cloud Brightening Project, one of the most advanced initiatives in the world. Their work focuses on engineering specialized nozzles capable of producing ultra-fine seawater droplets, tiny enough to act as effective cloud seeds. The challenge is precision. The droplets must be small enough to rise into clouds and increase reflectivity. but uniform enough to avoid unpredictable side effects. Meanwhile, in Australia, researchers at Southern Cross University have tested whether MCB can shield one of Earth's most fragile ecosystems, the Great Barrier Reef. Rising sea temperatures cause mass coral bleaching, threatening an irreplaceable marine treasure. By deploying sprayers from ships, they explored whether brighter clouds could create temporary shade over reef waters, lowering temperatures just enough to give corals a fighting chance. Private organizations are also stepping in. Groups like Silver Lining are pushing for controlled trials of cloud brightening, not as a silver bullet, but as one piece of a broader climate-resilient strategy. They argue that humanity must at least understand the potential of MCB before the climate crisis deepens further. In 2023, the first outdoor tests in California marked a milestone. Using a land-based sprayer system, scientists released mist into the air and measured how the particles formed and interacted. The results were intriguing. Particles behaved as expected, but the leap from a few localized tests to planetary-scale cooling remains immense. Key takeaway number 2: cheaper and faster than giant space mirrors. When people imagine geoengineering, they often picture colossal, sci-fi solutions like a 2,000-kilometer-wide sunshade orbiting Earth, blocking a fraction of sunlight. While dramatic, such ideas come with staggering costs, massive engineering challenges, and the kind of political coordination the world rarely achieves. In comparison, marine cloud brightening looks almost modest. It doesn't require rockets, orbital construction, or trillion-dollar megastructures. Instead, it uses something Earth already provides in abundance: seawater. With the right technology, that seawater can be sprayed into the atmosphere as microscopic droplets, transforming ordinary marine clouds into brighter, more reflective shields. The infrastructure is simple: ships, sprayers, and monitoring systems. Far closer to today's engineering capabilities than building space-based megaprojects. Another advantage is scalability. Unlike a giant space mirror that has to work at full capacity from day one, cloud brightening can be tested locally, one region at a time. Researchers can study its effects on small patches of ocean before deciding whether to expand. If something goes wrong, the intervention can be paused, and the effects dissipate relatively quickly. That reversibility makes it a far safer candidate for near-term experimentation than many other geoengineering proposals. Then there's cost. Early estimates suggest that running a global marine cloud brightening program might cost on the order of $5 to $10 billion per year. That's not pocket change. But in the context of global spending, it's surprisingly small. By comparison, climate disasters already cost hundreds of billions annually, and global military budgets exceed $2 trillion a year. For a fraction of that, MCB could offer a planetary-scale cooling effect. Engineering the clouds. So how do you actually brighten clouds? Turning theory into practice requires more than just ideas. It takes engineering that can operate continuously, reliably, and safely across vast stretches of ocean. The leading concept is the spray ship. Imagine an autonomous vessel powered by clean energy, equipped with rows of upward-facing nozzles. These nozzles are designed to spray ultra-fine seawater mist into the atmosphere around the clock. As the ship moves, it leaves behind an invisible trail of microscopic droplets. Wind carry those particles upward, where they blend into low-lying marine clouds, seeding new droplets and making the clouds brighter and more reflective. But ships aren't the only idea on the table. Some researchers envisioned fleets of drones capable of doing the same job with greater maneuverability, while others propose coastal spray stations fixed to shorelines, pumping mist into the sky over strategic marine regions. Each approach has its own pros and cons, from cost to scalability to maintenance. The biggest challenge, however, is precision. The droplet size must be almost exact, around 0.2 microns in diameter. Too large and the droplets quickly fall back to Earth as rain, having little effect. Too small and they fail to act as cloud condensation nuclei, drifting uselessly away. Hitting that sweet spot requires advanced nozzle design and fine control over spray pressure, particle distribution, and environmental conditions. Scaling this up would require not just one or two ships, but dozens, perhaps even hundreds, strategically deployed across the Pacific, Indian, and Southern Oceans. These regions are home to vast marine cloud decks, making them prime candidates for brightening. If coordinated, such a fleet could effectively dial up Earth's reflectivity, region by region, cloud by cloud. Risks and uncertainties. This is where the conversation turns controversial. Marine cloud brightening may sound elegant in theory, but the reality is far messier. Every potential benefit comes paired with a set of risks and unknowns that scientists are still working to understand. One of the biggest concerns is weather disruption. Clouds don't just reflect sunlight, they shape rainfall, wind, and regional climate systems. Brightening clouds over one stretch of ocean might cool nearby waters, but could also shift rainfall patterns thousands of kilometers away. That could mean fewer storms in one region, but harsher droughts in another. In a world already struggling with water scarcity, even small shifts in precipitation could have massive humanitarian consequences. There's also the issue of regional inequality. Climate change itself is unfair. Some nations contribute the most emissions, while others suffer the worst effects. Geoengineering could double down on that inequity. Imagine one country benefiting from cooler summers while another suddenly loses vital monsoon rains. Whose needs take priority? Who decides what trade-offs are acceptable? Then comes the danger of termination shock. If the world became dependent on marine cloud brightening to offset warming, and the system suddenly stopped, whether due to politics, cost, or conflict, the planet could heat rapidly in just a few years. That kind of abrupt spike would be even harder to adapt to than the steady warming we face today. And finally, there's politics. Who gets to control the thermostat of Earth? Is it the United Nations? A coalition of superpowers? Or could private groups take matters into their own hands? The governance question is unresolved, and perhaps the most dangerous uncertainty of all. Scientists stress one point above all. Marine cloud brightening is not a substitute for cutting emissions. At best, it's a temporary measure, a way to buy time while humanity addresses the root problem of fossil fuels. Key takeaway number 3: local tests, global effects. One of the most appealing aspects of marine cloud brightening is that it can, in theory, be tested on small scales before being rolled out globally. Unlike a space mirror or stratospheric aerosol injection, which demand massive infrastructure and operate planet-wide from day one, MCB can begin with local experiments. A fleet of ships could brighten clouds over a single reef, a stretch of coastline, or a regional patch of ocean, giving scientists the chance to observe measurable effects in real time. For example, shading a coral reef could reduce bleaching during a heat wave, or brightening clouds near a coastal city might blunt extreme heat for a summer. But there's a catch. The atmosphere doesn't respect human boundaries. Clouds move, winds shift, ocean currents ripple outward. A small-scale deployment might start locally, but once scaled up, its influence spreads across the planet. What begins as a test over the Pacific or Indian Ocean could alter rainfall in Africa, disrupt monsoons in Asia, or change storm tracks in North America. That interconnectedness is what makes MCB powerful, but also deeply complicated. This reality raises a critical point. International cooperation is not optional, it's essential. If one country unilaterally brightens its skies, others could feel the consequences. Yet right now, the science is moving faster than the diplomacy. Research groups are refining nozzles, modeling effects, and running field trials. But global agreements on how, when, and by whom such technologies should be used remain vague or non-existent. The core takeaway is clear. Marine cloud brightening may be local in execution, but its outcomes are global. Without coordinated governance, the risks of political conflict could rival the risks of the climate crisis itself. The future vision. If marine cloud brightening proves both safe and effective, its potential applications are striking. Imagine cooling regional hotspots like the Arctic, where rising temperatures accelerate ice melt and open the door to runaway climate feedbacks. By brightening clouds over northern oceans, scientists could slow the loss of sea ice, stabilizing one of the planet's most critical climate regulators. Or picture deploying MCB above vulnerable ecosystems like coral reefs. During extreme marine heat waves, brighter clouds could create temporary shade over reef waters, lowering temperatures by even a degree or two, enough to reduce bleaching events and preserve biodiversity. For regions on the brink of ecological collapse, this tool could buy years, even decades of resilience. On a global scale, MCB could function like a planetary air conditioner. Not a cure, not a permanent fix, but a stopgap that buys humanity time. Time to slash emissions, scale up renewables, and build the carbon removal systems that will ultimately be necessary. It doesn't replace the hard work of decarbonization, but it could ease the pressure while we get there. Some researchers even envision something more futuristic, a climate-controlled dashboard, where international agencies monitor and adjust Earth's reflectivity in real time. In this vision, cloud brightening could be fine-tuned like a dial, slightly increasing brightness in one region, dialing it back in another, balancing planetary energy flow with precision. But that vision also raises a profound ethical dilemma. Do we really want to take control of the clouds themselves? Is it wise for humanity to place its hands directly on the levers of the climate system? Marine cloud brightening offers hope, but also forces us to ask the hardest question of all. Not just can we do it, but should we? Marine cloud brightening is elegant, fast, and potentially powerful, but it's also untested, risky, and politically explosive. It could be humanity's emergency parachute, or a Pandora's box we can't close. So what do you think? Should we engineer the sky to save ourselves, or is that one step too far? Subscribe for more future tech deep dives and tell us in the comments. Would you trust scientists to control the clouds above your head? Stay blessed and stay curious.